Hi, I'm Dick Collins. This is one of a series of Airfax tapes on why things are important in relation to our flying. We'll also take a look at how to better manage the risks of flying.
If you like things in logical order, this tape on departing follows one on what we do when getting ready to fly and precedes one on the en route climb and cruise portion of a flight. Once all the pre-flight work is done, it's time to fly away. First, let's consider for a moment that this is an IFR flight leaving from Class G uncontrolled airspace. We might get our clearance in the airplane, on the radio, or we might have to get it on the telephone. Either way, the controller is likely to ask how long before we'll be ready to take off. If it is a phone clearance, and we first pre-flighted the airplane, arranged charts and everything, and even run the checklist up to the point where we turn on the electrical power, it's possible to give an accurate estimate. If it's a clearance on the radio, regardless of the class airspace, having everything done before calling for clearance makes it work that much smoother. Whichever way we get the clearance, do set up the avionics for departure before taxiing. Whether VFR or IFR, when taxiing out, make sure the turn coordinator or turn needle, as well as the directional gyro or HSI, is working properly. Just have a glance when you make a turn. If your checklist is arranged like mine, there's not a lot to do at run-up other than check the engine as per the checklist. All the rest of the items were handled before taxiing. If there's to be any delay for takeoff, don't taxi into position at an uncontrolled airport. And if there's a tower and the instruction is to taxi into position and hold, consider holding askew enough to be able to see the final approach course, especially in conditions of low visibility or if the departure is from an intersection. No, the controller is not supposed to let someone land on top of you, but it has happened. It's a good idea to have a final checklist to double-check the critical items immediately before takeoff. I have always used I can fly this puppy if the instruments, controls, fuel, trim, and prop are all okay. ICFTP. Get it? Oh well, it's corny, but it works fine for me. There are a couple of other things to double-check, but for the moment, let's look at those. Instruments means everything is perfect, in the green or working properly. Controls means checking to full travel and looking at them to make certain they move in the correct direction. Fuel means the selector is on a tank with adequate fuel. Trim means that the trim is set properly for takeoff. Prop means the control is full forward, given a constant speed prop. Neglect of these items has led to extremely serious accidents. On an airplane that requires flaps for takeoff, they need another check, and it's good to make certain your seat is latched. I hesitate to use the term, but professional pilots often refer to these last checks as relating to the killer items. We all consider the takeoff to be simpler than the landing, and certainly passengers are not as impressed by successful takeoffs as by perfect landings. They should be, though, because there are about equal numbers of serious accidents on takeoffs as landings. Landings do have more fender benders, so takeoffs are serious business too. Smooth acceleration to the proper speed, flawless directional control, a perfect rotation to the flying attitude, and an efficient initial climb make the transition to flight graceful and rewarding. Engine failures on takeoff are not desirable happenings in singles or twins, so risk management on takeoff has a lot to do with the power. The way we apply power to piston engines is important. Gentle throttle action is the key. Jamming a throttle forward can result in engine damage, and the bigger and more complicated the engine, the greater the need for gentle throttle action. Abruptly advancing the throttle on a turbocharged engine can result in serious engine damage due to overboosting. Something else that should be avoided is advancing the power while turning onto the runway. This can result in a side load on the landing gear, and in some airplanes, without the tanks full, a quick accelerating turn might move fuel enough to one side in the tank that it is away from the line that feeds the engine. That could result in a power interruption at or shortly after liftoff. When we fly away, we're taking what was dormant a few minutes ago and then asking it to develop a lot of horsepower and bring all the accessories up to speed. We're asking the old engine to go from idle to maximum on everything in just a brief moment. Certainly we don't have a lot of time on takeoff to monitor the instrument panel, but once the power is set, there is time to make a quick survey and abort the takeoff if anything doesn't look perfect. If the run-up was successful, everything should be okay, but a run-up and an application of full power are two different things. What might we catch? If the airplane has an EGT, you should know the normal EGT reading at full power and with the mixture set for takeoff, usually full rich. If the EGT is not normal, something is amiss in the combustion process. And if you use the conservative method of calculating minimum runway length, 2.2 times the POH number, there should be plenty of room to abort the takeoff and stop. The EGT would show an abnormal reading were a piston engine to have some jet fuel pumped into its tanks. Any abnormality in fuel flow would also be obvious. Another thing to check is the prop RPM. If it's a fixed pitch prop, you should know the expected RPM at the beginning of the takeoff run. If it's a constant speed, it should spin right up to the red line. If it doesn't, chances are the pilot missed something on the checklist twice and the prop control isn't full forward. If this is the case, the prop control shouldn't be abruptly jammed forward. Either move it forward smoothly or abort the takeoff and do it all over again. If the original checklist work was done that poorly, perhaps it should all be done again. Everything else can be checked at a glance. All accessories working, everything in the green. We do have a unique risk management opportunity on a takeoff. It is the option not to take off if everything isn't just right. Think of it the way airline pilots do. They have the majority of their takeoff roll in which to abort if something goes wrong, all because their takeoff planning is, by law, very conservative. Sounds and smells count as the takeoff roll has begun, too. Any unusual noise or smell would be cause to discontinue the takeoff and investigate. Choosing a conservative minimum runway length for takeoff has given us a wonderful option, the chance to abort in the takeoff roll if everything isn't perfect. We also eyeballed a point halfway down the runway and made a mental note that the airplane should reach flying speed there. If it doesn't reach flying speed by that point and you keep trying, any abort would be a brake smoker and eventually a trip off the end. You do, however, have to ask yourself whether you'd prefer to go off the end of the runway at low speed while slowing down or hit the tree halfway up. You also have to be realistic when judging acceleration. An airliner was once lost on a takeoff on an icy runway when the airplane had rolled almost 5,000 feet past the point where it should have reached rotation speed. The takeoff was aborted unsuccessfully at that point. The brakes were locked from the beginning of the takeoff on the icy runway, and the tires all blew as the powerful engines managed to make the airplane accelerate. The POH on most light airplanes doesn't do a very scientific job of telling us the proper speed for liftoff. The POH for my 210, for example, says to lift the nose wheel at 65 to 70 knots. 65 works only at very lightweight, and 70 doesn't work that well at heavier weights. The fact is the airplane stalls at from 63 to 68 knots with takeoff flaps, depending on CG location, so the liftoff speed in the POH is indeed on the low side. If 1.2 times the stalling speed is used, which is also the best angle of climb speed, rotation speed varies from 68 knots at 3,000 pounds takeoff weight up to 78 knots at 4,000 pounds maximum takeoff weight. By using my calculated speeds, I think I get better performance and more consistent liftoffs. Certainly trying to make it fly at 70 knots at maximum weight results in some high aerodynamic drag time with the nose wheel off the ground and the main still rolling. Trying to lift off too early can also cause directional control problems in a crosswind, especially in some airplanes. A Cessna with springs providing the nose wheel steering will have some rudder deflected when the nose wheel is lifted off the runway. The steering authority does not change much. A Cherokee, on the other hand, has direct linkage nose wheel steering, and the authority goes from a lot to a little when the nose wheel is lifted off. That's why a little extra speed is good for a crosswind takeoff, so the airplane flies eagerly away at liftoff. Something that usually happens right after liftoff has become a factor in too many serious accidents. The cabin door or baggage door comes open. If these are not properly closed, they will usually pop open at or right after liftoff. If it happens before liftoff and the conservative minimum runway length was used, the takeoff should be aborted. It depends on the airplane, but on most you can count on a lot of noise, perhaps some buffeting, and a little yaw when the cabin door comes open in flight. The door will generally be held open a couple of inches by the airflow, and there's likely enough suction to pull loose and light items out of the cockpit. The airplane, though, will be flyable, and it should be flown normally around the airport and landed. Then chastise yourself for poor checklist work and carefully prepare to fly away again. The same procedure works for baggage doors. Make a normal pattern, land, and close the door. The trouble comes when a pilot tries to rush the trip around the pattern, making steep, low-level turns. It may not be easy to treat a noisy condition like this as normal, but that's how it's best treated. There is a procedure for closing the door in flight in the POH of some airplanes. This should be used with care, with special attention to airspeed and altitude, because when there's a related accident, it is usually of the stall-spin variety. If the airspeed seems affected by the door being open and perhaps bothering the airflow of the static ports, fly the approach at the normal pitch attitude. Back to normal. Once off the ground, it's best to leave the power at full until 1,000 feet above the ground. A lot of pilots feel that best angle of climb speed is too slow and use best rate. That's okay. Both are good climb speeds. The main thing is that the options, in case of trouble, expand rapidly with altitude. If you're flying a retractable, when is it time to retract the landing gear? One school of thought says it should be retracted when there's insufficient runway left for landing. The other says it should be retracted when you have a positive rate of climb. Personally, I usually do the latter because my airplane climbs so much better with the gear up, and I'd rather have the altitude than sacrificing some feet by leaving the gear down for the remote possibility of an engine failure. Where the engine too failed, the altitude might be of a lot more value. Plus, I leave the airport at a higher altitude, giving those folks who built houses off the end of the runway less to gripe about. An old, very old FAA study suggested that most engine failures occur when the power is changed. That used to be one reason to leave the power alone for a while after takeoff. More recent information shows that this isn't necessarily so, but flying with full power to at least 1,000 feet is still valid because of the increasing options as you go higher. When does the option become one of returning to the airport after a complete power failure? It depends on the airplane, plus other things: wind, the length of the runway from which you departed, and your skill at flying the airplane in a very demanding situation. The primary accident result in such an attempt is a stall spin, which is almost always a serious event. Let's look at how much altitude it might take. We'll use my 210 as an example first. With takeoff flaps, the airplane stalls at from 75 to 81 knots, depending on CG, in a power-off, 45-degree bank turn at maximum takeoff weight. That means that 100 to 105 knots is the minimum speed in the turn. At the best glide speed of between 85 and 90 knots, the airplane descends at about 1,000 feet a minute, power off. In the turn, it would descend at between 1,500 and 2,000 feet per minute, or even more. Though the turn would take as few as 20 or 30 seconds, that would use up a lot of altitude. Some would have to be used for maneuvering for landing back on the runway, too, because the 180 would not leave the airplane lined up with the runway. Then the rate of descent must be arrested because, even with the cushioning effect of the landing gear, a touchdown at a rate of descent over 500 to 700 feet per minute can be harmful to your health, to say nothing of the airplanes. Incidentally, if a turn were to be attempted and there's a crosswind, it would best be made into the wind. Also, with a strong wind down the runway, any landing after a successful turn would be downwind. It can take a lot of altitude to turn around, even in a lighter airplane. We'll show it to you here in a Cessna 172. We've calculated 1.3 times the stalling speed in a 45-degree bank. When the power is pulled back, it takes a quick lowering of the nose just to maintain the climb speed, and even more to increase the speed for the turn. As the airplane comes around in the turn, you'll see that it's not lined up with the runway, and by the time we maneuver it back over the runway, we've used up most all the 1,000 feet of altitude with which we started, and we were expecting the power to fail. There would be a strong startle factor were it to happen out of the blue. One of the primary reasons the rule of thumb is to not try to turn around is because of that high incidence of stall spin accidents during such attempts. These result from a pilot trying to rush the turn, making the bank too steep, and not maintaining airspeed. Actually, the chance for success is probably better in a 30-degree bank. The increase in induced drag is 3 times as high in a 45-degree bank as in a 30-degree bank. Aerodynamics for Naval Aviators, an excellent text, puts it thusly: no appreciable change in load factors or stall speed occurs at bank angles less than 30 degrees. Above 45 degrees of bank, the increase in load factor and stall speed is quite rapid. This fact emphasizes the need for avoiding steep turns at low airspeeds. Low-altitude turning flight is always risky. Power off trying to turn back to a runway is probably the riskiest low-altitude turn. So, what are the alternatives to turning around? The word is usually to pick the best spot ahead, or at least the spot that requires the least turning to reach. At some airports, there are few attractive places to go, and certainly a pilot should always strive to minimize any hazard to people on the ground. The better news is that if the forces in a crash landing are spread over just a little distance, then the event can be survivable. Our belt systems are designed around a 9G requirement, meaning that they should hold us in place during a 9G deceleration. It's probably not likely that you'd ever get an even deceleration in an off-airport landing, unless it were in a cornfield or something like that. But if you did, flying an airplane like a 150 or 172, an even 9G deceleration from a minimum speed touchdown would take less than 15 feet. In a heavy single, it would take between 25 and 30 feet. Ground speed is the key, which means landing into any wind enhances the prospects. Also try to hit things with the wings, not the fuselage. When we were talking about crosswind takeoffs, the need for extra speed at liftoff was mentioned. The reason this is so important is that you don't want the airplane to touch back down again, especially if any drift develops after liftoff. The reason it might do this would be the crosswind shifting to more of a tailwind direction or the speed of the wind changing. That could affect the airspeed, and even though the airplane is on the ground during the takeoff roll, the name of the game for liftoff is airspeed. Soft fields are well covered in the private pilot training process, but there are some things to watch. Actually, most of us don't fly from airports that are soft, but a lot of us do fly in the winter in country where snow is a possibility, and we may need to take off on a snow-covered runway. That is a time to apply the principles of a soft field takeoff. One question that's often asked is, how much snow can I take off in? If the snow is greater than half the diameter of the nose wheel tire, or of the main gear tires on a tailwheel airplane, you probably don't have a chance unless it's extremely light snow. There's no way to calculate the effect of snow on a takeoff roll, so the best thing to do is eyeball a point halfway down the runway and resolve to abort the takeoff if flying speed isn't reached by that point. Also, you'll need to drive down the runway first to make certain there are no drifts. If there's a strong crosswind on a snow-covered runway or one with ice patches, taking off is a bad idea. You might not have adequate control authority to keep the airplane going down the runway and pointed down the runway on the slicker spots. If a little sideways action develops on the slick, going back to drive pavement can be thrilling. One final item on snow. We all know to clear all the snow, ice, and frost off an airplane before takeoff. If it is still snowing, though, enough might accumulate during taxi to be a factor. This would be especially true were there to be a delay. On a soft field, we use the maximum flaps allowed by the POH, lift the nose earlier in the run, and use the lift that generates with airspeed to lighten the weight on the main gear. After liftoff, it's level flying to accelerate to normal climb speed while disposing of the flaps per the POH. If the airplane has an extremely powerful elevator, you may not want to use it all because the liftoff attitude can become extreme and the airplane might not want to accelerate. Certainly you wouldn't want to get it out of ground effect in an extreme nose-up attitude. For a short field, the technique is well known. Full power before brake release and a liftoff and climb at the best angle of climb speed. We do have to be very conscious of wind on a short field. How will it affect the performance of the airplane? This is where you want to really visualize the wind flow over the terrain and obstructions and not try to fly if it appears that the wind flow will affect performance. If you use that conservative number for required runway length, this may take care of itself. On any takeoff, but especially from uncontrolled airports, get an idea of traffic from the radio as well as from a search of the sky before rolling. Be especially alert for aircraft using a different runway, especially if you can't see the other end of your runway or any other runways at the airport. Announce what you're doing and then search the sky as you climb. Remember that in Class G airspace, it's perfectly legal for airplanes to be out there with but a mild visibility.
Well, that gets us up and off the ground. Thanks for flying with us on this tape, and in the next tape, we'll be looking at getting on up to altitude and taking care of en route chores. If you think there's nothing to do en route, just think about it a little bit. There's a lot to do, and if you stay busy, the miles pass faster. Thanks for flying with us, and fly safely.